All right, so now I will introduce our speaker for today. Lacazette will be talking about finding and simulating hot sedimentary aquifer geothermal prospects in the geothermal basin. I have his bio. So Lacazette is an internationally recognized expert in structural geology, natural rock fracture systems, and the interaction between hydraulic fractures with natural fractures, interpretation of passive seismic and microseismic data, borehole imaging, fracture density and orientation statistics, and chemical and mechanical interplays of fluid rock interaction, and sedimentary geothermal systems. He's the author of 35 plus papers on all of these and other subjects, wrote the technical specifications for the borehole imaging and orientation statistics modules of 2 major software packages, and holds patents on passive seismic imaging and new structural seismic attribute. He has over 30 years of domestic and international experience in 26 different countries, with oil and gas operating with Texaco and EQT, and service with Western Atlas, Baker Hughes, Golder Associate, Global Geophysical Services, and other companies. And as an independent consultant for numerous companies in exploration, production, reservoir characterization, R&D, software development, business development, and core and outcrop analog studies. Al's professional activities have focused on American Association of Petroleum Geologists, where he served 2 terms as Reservoir Development Committee, 6 terms as an associate editor of AAPG Bulletin, is a Charles H. Taylor Fellow of AAPG, and a founding member of AAPG's Petroleum Structure and Geomechanics Division. Al helped develop the next generation of geoscientists as an affiliate professor at the Colorado School of Mines. Al received a BS and an MS in geology from the University of Kentucky and his PhD in geoscience from Penn State. So he does it all, and he's here to tell us about it. Thank you, Al.
Eric shows a much younger picture of me for this. Quite, so how do I point with this?
The laser pointer isn't going to work, but the up and down arrows do. Because it's a
Laser works on TV.
yeah, that's the thing. Is the laser doesn't show up on the TV, but the arrows will work. So
You'd have pad on there.
if you want to point at certain things here, Al, we can set up the laser pointer on the touchpad.
Okay,
You could come over and do that, but then that will advance the slides.
cool. Right, so this is what this presentation is very much a team effort. I'm talking, but these other folks contributed. I don't do all of the things I'm going to be talking about. Jim Hollis and Fight Matter are here. So let's get going. So a little bit about geothermal technologies. We will be the wells for our first project will be in Wattenberg. We've got permits. These are the first deep geothermal well permits that were granted by the state of Colorado. We've got landowner agreements in place, collaborative technical efforts with large oil and gas companies. We've got a substantial intellectual property portfolio, and our technology is designed to optimize longevity of wells, which improves the economics, so lower cost power. We recently received 1.25 million in grants from the state of Colorado, and we are currently raising capital if anybody's interested. About sedimentary geothermal systems, this is the new term. We formerly called them hot sedimentary aquifer geothermal systems. It's about exploiting porous permeable rock, and but lower temperature, because once the temperature gets above 150 C, cementation takes over and you lose the permeability. So it's got to be cooler. But the modern biomass cycle power plants enable economic electricity production. And with modern drilling, we could get high flow rates. And there's one of the key things is that there's tons of data in oil and gas cases, as I will show. And the forest scale fluid flow extracts heat very efficiently. In a frac, like in EGS, the fluid flows in the fracture, but rock is an insulator. So the fracture surface cools off and you get heat stranded back in the rock block. But when you're flowing water through the rock at the pore scale, you only have to conduct heat over the diameter of the sand grain. So the extraction is very efficient. And this gives us long well life and good economics. So let's look at the issue of abundance. This is an Energy Information Agency map of geothermal plants in the US. This is an NREL map of potential hydrothermal and EGS sites. So the yellow dots are potential hydrothermal sites. And the shading shows potential EGS sites. But again, there's issues with EGS that we don't have with hot sedimentary aquifer or sedimentary geothermal systems. Sedimentary basins are pretty widespread in the United States. And if you look at the oil and gas wells, each one of these dots is a well. It's a USGS map of all the oil and gas wells in the country. Each one of those wells is data. Now, in geothermal, data is hard to come by, right? It's expensive. People say, oh, seismic is too expensive for geothermal, but it's not too expensive if someone else has already shot it. Okay? So the status of our present project, which I'm going to talk about, is that the wells are permitted. We've got the landowner agreements and everything. I have to make it got slide must have slipped in there. Sorry. So location maps. So this is the state of Colorado, and I've drawn the inner and outer Colorado mineral belts. And it extends off into Wattenberg. And those red lines are wrench faults, strike slip faults, whatever you want to call them. And the red is the Wattenberg hotspot. Dotted outline is Weld County, where we're going to be working. Zooming in a little bit, location map, there's in the ellipse is where we are, Weld County outline. Those red dots are hot springs, so you can see the trend of the mineral belt going up into Wattenberg. The Denver Basin stratigraphy, painting with a broad brush. That purple up at the top is the Pierre Shale, which is a thick seal. Above that, you've got a hydrostatic, pretty much hydrostatic pore pressure gradient to the surface. Below that, in green, we have a self-sealing, self-sourcing hydrocarbon system that is in Niobrara and Codell, and sometimes some other formations that are the main producers. But below that, it's under pressure. And a lot of people don't realize that. It's not overpressure, the Denver Basin's overpressure. No, it's the Muddy J, the Dakota J sandstone there is quite permeable. And as I'll show in the next couple of slides, it drains eastward. So, but there's a number of potential aquifers down in the Paleozoic section. I have them in yellow there. But in red, you have the Lion sandstone, which is what we're going to be focusing on. So looking at the pressure regime a little bit more, there's my cartoon on the left there. We have in blue the seal, and the Permian section, which is the Lions is a Permian unit there, and we get recharge along the mountain front of water that flows eastward. And so this lower right picture is from the literature. This is from Nelson's Nelson's paper. And he's got the topographic profile and the pressure profile, and this lower Cretaceous aquifer. It comes up to the surface in western Kansas and Nebraska. And so so it's under pressure. And the pressure data that we have shows from an oil field within 2 or 3 kilometers of our prospect that the potentiometric surface is at about the same elevation as the topography in western Kansas. So it looks like the water is not moving much right now. A couple of things about the Lions. It's an important source of building stone where it crops out of the mountain front. A lot of buildings around here are made of it. It hosts 8 oil fields in small anticlines, but it's wet almost everywhere else. in the study area, really throughout the basin, particularly in our study area, it was the edge of an erg, a sand sea, like in Saudi Arabia. And the environment was very similar to the western Persian Gulf now, the south environment. So you have desert sands being cemented up with calcite and hydrogen. So this is the depth of the line's potentiometric surface below the ground. And this is important for economic development because you have to pump. So, you know, you don't want to pump too much. You want to know where you are and how much you're going to have to pump. It strongly affects the economics. So let's move on to identifying the prospect. Let's talk about the geothermal gradient temperature first. Well, we use bottom hole temperatures for oil and gas wells, but those have to be corrected for mud cooling. So I use the mud cooling correction curve, and then we compared it with a one-dimensional geothermal model that Fight did. And Fight made a thermal model of the rock by looking at the log data and estimating the thermal properties of the rock. And we took a corrected temperature, bottom hole temperature, and extrapolated it upwards. And then compared it to the case hole temperature log, which had been collected several months after the well was drilled, and should accurately reflect the formation temperatures. And as you can see, they match really well. So we're happy with our correction. So these are the geothermal gradients for our study area. We did a lot of work to make all these maps, so anybody who's recording this online is not going to be able to geographically register them with anything on the maps. But they look pretty good. So there's a hot area, right? And I'm going to show you a bunch of maps that are made with grid maps. So a map is just contoured, a contoured grid of points. And as long as the grids are all the same, we can multiply them and do mathematical operations on them. So if we take the grids, the geothermal maps, and multiply it by the depth to the formation, then we get the temperature at the top of the lines. So we get some pretty good temperatures here. We would like to have 120 degrees Celsius. And we've gotten better than that in a number of places. Porosity and diagenesis. So again, the Lions was deposited in a soft environment, and it was completely cemented up with anhydrite. So we have original dune sand porosity cemented up with anhydrite. Then the anhydrite cement prevented compaction over the long burial history of this Permian unit. Now, it resulted in cementation of quartz grain contacts. There was a lot of load on it, so you had a little bit of pressure solution at the quartz grain contacts, but that's it. There's a little bit of quartz overgrowth in places where the cement's been removed. But later, fluid flow came through and removed the anhydrite cement. So now we're left with a formation with original dune sand porosity and a strong welded skeleton. This is a great process. This is an old paper. This is a figure from an old paper by Lacazette et al. Showing the dissolution and precipitation of some of these diagenetic minerals. And we're in one of the fairways. So, but there have been a lot of wells drilled since then. There's been cores cut, logs collected. So we hired Mark Longman, well-known DJ Basin geologist, to do a proprietary petrographic study and update these Lacazette's results. And the study confirmed the earlier work, indicates that the permeability fairway may be actually a bit bigger than he mapped. So some of the slides. So the blue, the left side is plain polarized light, and the right is under cross colors, gypsum plate. And you can see the arrow there shows gypsum, shows a gypsum crystal overgrowing quartz crystal. So it's in crystallographic continuity. I didn't know this term, but we had a study down it. It's called polyclinic anhydrite crystal. It overgrows the grains, but it's being eaten away on the edges. And if we look at box cores, we have a data show at Chevron, and got to look at their at core from this oil field, just a few kilometers from our process. And this core is below the oil water contact, but you can see anhydrite, residual blebs of anhydrite. And a couple of them are marked with red arrows, and you're quite visible. So clean rock, but some residual anhydrite. So porosity permeability. So we have core plug data for both horizontal and vertical permeability and porosity. And so here's our porosity permeability transforms for horizontal and vertical perm. And so we have a quantitative relationship between porosity and permeability. Here's a pH map. So pH, we found that the density log porosity, closely matches the core results. So we use the density porosity logs just without correcting. And say the log has a sampling interval of 1 foot. Well, you take that porosity, you multiply it by 1 foot, and so you've got a fractional foot, and you add that up to the formation. And what you wind up with is the empty space in the formation. So this pH map shows the thickness of empty space in the formation. If you crush all the porosity out, it's how much water you get. For people with oil and gas background, this is familiar, but not everybody has that here, so I'm sure. So I'm explaining this. So we've got some pretty good pH here. You can do something similar with permeability. For each log interval, you use the porosity permeability transform that you got from the core, and you determine the permeability, multiply it by the thickness of each, the spacing of the log samples, and add them up, and you get what's called the flow capacity. And this only shows flow capacity. We didn't add anything in here if it wasn't greater than 40 milliliters. And again, pretty good flow capacity. So heat. Well, this is the heat capacity of the brine to lines, taking into account the brine salinity, the temperature mass, and the pressure that we have. Again, we have pressure data from a very nearby oil field. And so we have a heat capacity map, and we can use that along with the temperature map to determine the heat content of the brine. We make a map of that. And we can look at the heat content of the effective porosity. So we figure the effective porosity was better than 10%. So we're not going to, if the porosity is less than 10%, then maybe we can't, that we're not going to get much of that brine out. So you look at how much heat you have in the brine, but it's not just the brine. Remember, we're flowing water through the pore space of the rock. So how much heat is in the rock? Because we're going to get a lot of that out as we recirculate water. So we just take the thickness of the solid skeleton of the lines formation, which is the inverse of pH for the field. And And we can calculate, using a value for heat capacity value for sandstone similar to Lyons. We can look at the heat and solid skeleton of the rock. Now, notice that these maps look very different because you've got more heat in the brine where you've got more porosity, and more heat in the rock where you've got less porosity. Now, in the heat exchange of a binary cycle power plant, we figure there's going to be an 80-degree C temperature drop. So how much heat is available from the brine for an 80-degree C temperature drop? You make it out of that. Heat liberated by all the rock for an 80-degree C temperature drop. Heat liberated by the entire Lyons formation for an 80-degree C temperature drop. So we look at make a bunch of maps like this, and we can make other kinds of maps too. You can generate one of these maps in a matter of minutes. I use Surfer. It's a great piece of software, like golden software. So we chose the project location based on looking at the temperature, the rock quality, the available heat, proximity to data, because you don't want to get too far away from data, because it gets scary, and structure. Now, unfortunately, we have not raised enough money to have the size to get the seismic yet. So the structure is, what's in the literature that we have from the well data. And then we chose the location and permitted wells and went on to simulation. So we built, now we've got actually 3 simulation efforts. Fight is working on full system modeling simulation, which couples everything. It's got the power plant, the wells, the pumps, the formation, everything in it. But that's a single porosity, uniform porosity permeability system. We also have modeling like that going on by Saman at Johns Hopkins. And this, we hired Golder Associates to do a very detailed model. And we built a detailed 3D stratigraphic model. So Steve Kumel, our stratigrapher, looked at well data in the area, took density porosity logs, and built a grid of them. And we had to reuse some wells. And he identified stratigraphic horizons, which are those black lines. And then the color shows the porosity. And the porosities were interpolated throughout the entire 3D volume between each of those stratigraphic surfaces. So the interpolation only went on between the stratigraphic surfaces. And we got a very detailed 3D porosity line, which with the porosity permeability transforms, we could transform it into a permeability. And so we did a very detailed simulation. So this is what the well setup looks like. 2 well pairs, 2 long horizontal wells, side by side, an injector and a producer. And that blue one is, maybe it's going to be a pilot hole or a monitoring well, depends on our money raising, but this is the plan. Now, when you simulate, you find that you set up a pressure dipole circulation system. So what we're looking at here is flow velocity in color, and the streamlines and flow directions are shown by the arrows. So between the 2 wells, you get the highest velocities. But you're also sucking in water from elsewhere in the formation. And now this is for a 600-meter well space. We've made a lot of models. This is a horizontal slice of a fragment model after 20 years. So this is a slice at the depth of the 2 wells. And again, you're looking at the flow vectors and velocities, this time in cubic meters per minute. Now, but notice that here, the flow vectors are much more complex. Excuse me. if we go back to this model, which is a console model, uniform porosity permeability model, everything looks very nice and well organized. But here, it's a lot more complicated because we've got a complex porosity permeability structure. And you've got fluid coming up from below. But when we compare these two models, they're really similar in terms of produced fluid temperature versus time. So this is for 20 years. Now, these two models have different starting temperatures, but the Fragman model has a larger temperature drop over 20 years because of shortcutting through a high permeability stream in the model. But it's still, we've got great longevity in these wells. If we look at the sources of the produced fluids, the orange line is the reservoir fluid. So that's virgin reservoir fluid. And the blue line is re-injected water that's recirculated through the formation. And so this is volume versus time over 20 years. Now, to deal with the issue of shortcutting, like you saw in the Golden model, this is how we're intending to complete the wells. So an open hole completion with tubing and packers, open hole packers. And between the packers are ports that can be adjusted from the surface. Strapped along the outside of the tubing is a fiber optic cable with heaters. And this is a technique that is used successfully in oil and gas. It's relatively new, but it's in use. Oil and gas and water production. And with it, we can measure temperature and flow rate. You turn the heater on for a while, you turn it off. And you'll look at the temperature decay that you get from the fiber optic. And so we'll do the same thing with injectors in the injector and producer. So that we can deal with any shortcutting in fractures or hyperpermeability streams. Now, from the Fragman model, we can do particle tracking. So we can see what the footprint is. So red is where the fluid has come from into the producing well. And blue is where the injected water goes. So with this, we can know how much area we're affecting. So if we want to use doublets like this, so this is called doublet 2 wells, we can figure out how to space them so they interfere with each. But we're also doing a lot of other modeling with multi-well configurations that are also very good looking, better really than doublets. So in summary, this study gives you a workflow of exploring 4 hot sedimentary aquifers. It's really almost exactly the same as an oil and gas probe, except you're trying to not find oil. And but we can only get these rich data sets in oil and gas. It's already been collected. I mean, all this data is publicly available. Production data, for oil and gas is available. But you got the log data, and you can dig, if you want, you can dig it out yourself from the files at the CMC, or buy it from a database. And so exploring the sedimentary for these geothermal systems will greatly expand the potential for geothermal electricity production over what it is now. I mean, the potential area is vast that this can be done. Well, and with the vast volumes of water available in the long well lives, this looks very economical. It's low-hanging fruit, and it's been very frustrating to us that Geothermal Office does not fund this kind of work. Oh, we do sedimentary geothermal as long as it's at least 170 degrees C. Well, at that temperature, there's no porosity. I mean, you have to frack. So anyway, that's it. Some joints in the Lion sandstone.
Question, Kelly?
Sure.
Questions from anyone here?
We're going on the next surface. Surface.
No, the problem for distraction is we don't need pumps to inject. We need a pump to lift. And then, but the thing is, the water is going to be falling down the injector. So we can put a generator. Schlumberger sells, excuse me, SLB, sells these things. They're just ESPs wired backwards. So they're generated. And we can recover a meaningful amount of electricity in the injector.
So it's just pull it out. ESP or
With
something.
an ESP, yeah.
And let it go back in the injector.
Yeah. Yeah.
I have a couple of questions. With the anhydride inclusions that you have you mapped those extensively or just in the one core?
Well, we have the one quarter, but Lewandowski mapped them. And the, if you look at the density porosity law, it shows up there, right? I mean, you have poor porosity. We've got a lot of anhydrides. And with new seismic processing techniques involving AI, we think we should be able to extrapolate the high porosity around.
And then looking at that picture there and knowing something about the lines, did you figure any fractures into your model?
There's very little structure in here. I mean, this is.
There are ambient fractures,
There are.
whether you have structure or not.
Yeah, and I've worked passive seismic and borehole image data in and out of Aurora, but not lines. But that's a very different structural situation that we're involved in. We'll have to see. Once we start seismic, we'll look at things. We'll do diffraction imaging, and things like that for the progressives, and just look at the structure in detail. We try to create fractures. I spent my career working on this. Most of my career working on fractures in oil and gas reservoirs. So I think we can attack this problem. Yeah.
Question about what are your expected flow rates out of your producer?
100 liters a second.
Can you fix that number for the rest of American people?
That's how we roll the rates. So, yeah.
First, I would agree with you. I think the DOE should be funding more low temperature projects. That's over time. Not the fund. But then second, I wanted to ask, how important is your injector well for reservoir pressure?
Oh, crucial. Absolutely crucial. Yeah, well, I mean, one thing we need to flow anyway, for heat extraction. But, yeah, I mean, we need the pumps, right? I mean, so pressure support at the producer is very important. It's also important to prevent formation around it.
So that's why you have them so close together. It's 100 meters spacing is 1.5.
Well, we're talking about 600-800 meter spacing, maybe.
They're a kilometer apart. And the closer we move them, the more support that we get, we use the comparison to cost. Further than we have them away, they last. So it's optimization.
So your starting temperature is going to be, once again, you're talking about American, so
248, right?
248 or so. So have you done the math on a 5,000 foot lateral, 5,000 barrels a day with the binary system that can handle that temperature? Do you think you can get like 5-10 megawatts out of the well?
Yeah, well, we're 3.5 for a double, yeah.
Net,
But,
net, right?
Net post,
Yeah.
post parasitic and all of that.
Right. Right.
Surfer makes great 2D maps. Have you tried merging in those data sets together? The data layers, the data layers to see if you can come up with other answers? There is a methodology. for doing that.
Yeah, I mean, yeah, we play crazy stuff here. Sure. Yeah,
Thanks, Alex. So yeah, we targeted 123 C,
then,
and you have a threshold of 150, which so that speaks on.
Yeah.
Or is that?
no, I think just in general, let's try it. You know, it depends on how deep it is and what your thresher regime is, how low the temperature is, right? I mean, the binary pipeline manufacturer, system manufacturers saving money on 100 or even 90, but, we can draw probably people out of it. Then, you know, if you start looking at temperature versus permeability, you get close to 150, stuff's going down. So, you know.
One more.
Yeah.
Sorry.
Okay.
I'm that guy. So I think there might be someone here in the state of Colorado that worries about this, but I've drilled a bunch of wells in Colorado, oil and gas wells, and I think I showed the scars from doing that. Is it easier for you to think of geothermal well happen in Colorado than me, my oil and gas district?
It's about the same. I mean, I'm sorry. You just have to protect the aquifers on your way down and.
So do you have to worry about abandoning, since you're injecting in the lines, you have to worry about if there's your wells that go to the Niobrara or Codell, do you have to abandon those, like?
We just stay away from those, right?
Yeah.
I mean, we're just, we're drilling new wells because they're bigger.
Well, I understand that, but if there are historical wells, even if they're P and A, I always had to go back to P and A wells that were P and A even as recently as maybe 9 or 10 years ago. If I was gonna be fracking in the Niobrara.
Yeah.
We're not,
Lions, do you have to worry about that?
yeah, we're not fracking.
So,
So,
But you are injecting.
yeah,
Injecting. So we have to take water out and put it back in.
yeah.
we're not changing the volume.
So you're not gonna exceed frac barrier.
No.
Nope.
No.
So, one thing I noted during your discussion of your modeling of things you were flowing, you're assuming only flow from above and across the units. Did you assume that your heat flow is only from across the units or above? Or did you assume the entire line is from above?
I mean, in the simulation, the brine flows through the whole formation. I mean, you know, it has some preferred routes, yes. More in some direct places than others. But yes, it's
But you also expect heat from the above and below.
It's not fast enough to.
Over 10, 20 years, yes.
The water is hot enough as it is. So a lot of people. Got 30-inch stake. Too, and there's insulation on the top and hot rock.
yeah, it's pretty well sealed. I mean,
Hydraulically steel, but thermally it's still.
yeah, it's firm. You know, there's a couple of thermal conductors, but they're not permanent. I mean, you've got an anhydride on top of mine, so it's well sealed. The shales with the tank underneath the lines are good seals. That makes a lot of sense.
What's the TDS of your farm?
120,000 ppm. No, or use higher. You know, you talk to the geologists that work the oil and gas lines, and they tell me that they think the salinity is higher in the ambient, which is where we have most of the water sampling. So. Okay.
This mostly is two of this. I'm curious about residual gas, so there are some oil formations.
Right.
The places that are in the upper part of the lines. Is there residual gas in the formation?
I'm sure there's going to be some residual gas in the brine. I have a bunch of, logical mass spectrometer drilling gas logs from deep injection wells that pass through the lines. And where the lines have no oil, but yeah, it's got some hydrocarbon gas. Now, your logical mass spec logs are qualitative, not quantitative, so we don't know how much, but we're expecting some hydrocarbons. If there's enough, then we might separate it out at the surface, burn it, heat the geothermal fluid even more, and send the CO2 back down with the injected water. So there's no CO2 release. This is being done in Canada. You use a membrane separator, so you use your oxygen, so you have to send nitrogen down there as well. But yeah, that could be good.
I think you said your double well spacing is 600 meters?
We modeled a bunch of different things, 600, 800 kilometers,
Yeah, I was just wondering.
yeah, well, it's just like, there's trade-offs against well length and spacing. There's a lot to consider.
So you optimize it basically by changing the well length, which impacts the economics of it, and then the separation, and you minimize parasitic power and maximize those. So it's multi-variable conversion. Yeah, cool.
Yep.
You showed an interesting rifle flowing pattern, and sorry, misunderstanding, but, you want to prevent some shortcuts. You showed a slide about that. How much is it also possible to produce some fractures in the surrounding area that would enhance the flow in the surrounding area, sort of like the shortcuts?
Yeah, well, right, I mean, short-range through fractures is definitely a concern. But we'll run into this when we drill those levels. We'll know where they are, and then with flow data from the fiber optic cables, we'll be able to see where short-range is and control that.
The question on kind of your broader perspective on the geothermal potential in the Basin, right? So your whole idea in testing is to do with not actually hydraulic fracturing wells and leveraging that possibility. And one of the effects on the energy level systems of hydraulic fracturing, you see that as not having great area. Why is that out?
Well, the thing with EGS is that basically, there's a number of these guys. It's expensive, right? Fracking is expensive. So, we're saving money by not fracking. Also, it's, geothermal is green energy, right? And people like that. And, we fight with what the F word, but you also make it a short term. So, I mean, in Titan, there's a number of potential plays like this in the DJ Basin in different formations. I only talk about we're looking at a number of other prospects that I'm not going to tell you. But that means this is public, right? We permitted the well, so everybody knows where it is. But yeah, there's a number of other permeable sandstone units, and you have this complex temperature structure in the basin. But it's a matter of you have to evaluate everything: pressure, porosity, permeability, depth. I look at it all to find good places. Yep.
Gases to look like in the reservoir.
Some methane, ethane, it's really, yes, just basic hydrocarbon gases. Yep.
There's what apologize for fluid loss to expect.
None. Yeah, it comes out around, goes through the heat exchanger, goes back in information. Or if you have skill or something like that, which could be minor, shouldn't be anything lost.
All right, I'll have a few questions online to pose to you.
Sure.
Thank you. Number one, what would the flow rates do to the two simulations?
100 meters a second.
Both simulations?
Yeah.
Have you been, have there been any brine samples collected and any lithium?
So, yeah, we got brine samples from oil and gas fields very nearby. We've analyzed them for lithium, and the lithium content is way subeconomic. So, like 16 ppm and 22 ppm, we got it. So,
The third question, what's next for the prospect? Do you have any indication of what is holding up investment in the projects?
Talk to Jim, you answer that question.
Yeah, so the utility companies don't want to do the first one because it's not proven. So we pivoted into the data center and make progress.
Thank you. Those are the questions online. Any other?
Audience, yep.
Now, what, you talk about how much you're flowing, how many megawatts you're talking about, what's your break-even point, to pay off the well bill? Is it, 3 years, is it 10 years?
It depends. Sorry, but it's, so the first one takes a little bit longer, then you keep trying to scale. So the process that Alex has about 3 years for 30 years. So if we build that whole thing up, we think we can get our costs down to 6 cents. Pay that 3 months. Yeah, I mean, it's small and water too, right? So you have to maintain these standards. Yeah.
Great. Other questions from the audience? Thanks, Al.
Just a few slides from the sponsor, if I could. I won't hold up a return to the bar for your second or third or however many round. I'll be quick. A note on the usefulness of being a geothermal rising membership in geothermal rising. Lots of access to important industry information and interface with the geothermal community. Geothermal Rising maintains one of the best and most comprehensive libraries of papers in referencing a wide variety of different topics in the geothermal industry that is accessible by GR members. And so if you are looking into and researching topics in the geothermal industry or hot topics and in geothermal in general, it is updated yearly after the Geothermal Rising Conference, and also interfaces with the IGA, the International Geothermal Association Library as well. So very comprehensive, very worthwhile database to be looking for your geothermal topics. And well, that's 2024-5, but I do need 2025 as the year when the next Geothermal Rising Conference that will be held in the annual conference this coming October, the 26th through 29th at the Peppermill Resort in Reno. It's been very well attended, particularly the last number of years, very exciting, lots of great topics, great discussions taking place about the near future of geothermal. So it's very informative. Hopefully that we see you there. And the fundraising message that we like to provide at the end of our discussions when we get together for these quarterly events for the Colorado Rig is that GR funds partly the Colorado Rig for these activities that we put together every quarter, the site visits that we do, the field visits that we do, and It's important to reach out to the community for that funding support that allows us to keep having activities and events like this. Of course, we also focus on putting together the holiday party. So now that everybody raised their hands and is attending the holiday party, that will help our funding too. With great events as we begin planning for events like this next year. Believe it or not, only about 3.5 months away from the end of 2025. So thank you again for the chance to get everybody together to present and to Lacazette for a great presentation. That's a wrap. I'll put up a couple slides for sponsors to GR, but if there's questions, please stay and grab another beer and hang out. Thanks.